In single variable calculus, you looked at functions that took a real variable from its domain and gave you a real variable for its range. This is the first real big part of multivariable calculus, is the functions we're going to look at take a real number, and this is actually usually represented by t, and it gives us out a vector in R2, usually an x and a y. Now you've seen a little bit of this already in Calc 2 when you looked at parametric equations. So parametric equations really are, we're going to use the terminology vector valued functions. We say vector valued because the value we get out in the range is a vector. It's a point in the plane or in the space. So let's look at a couple examples. Let's say we have the function r of t. Now we denote this r with a vector over the top, indicating that the value we get out in the range is a vector. So let's say this is 2 cosine t, 2 sine t, and t. So if we were to ignore the t, if we were just to get rid of this last coordinate in here, we would see that x equals 2 cosine t, y equals 2 sine t. And if we eliminate the parameter, you see that gives you this circle of radius 2. Imagine that's a circle. A circle of radius 2. So we've got 2 in the x and the y. So we've got the circle of radius 2. Now as we trace this circle out, the z value increases. So if we were to look at at my attempt in 3 dimensions, so this is x, this is y, this is z. So as we start tracing out, we start out at t equals 0. If t is 0, the x coordinate is 2, the y and the z are both 0, so we're going to start on the x-axis. We're going to wrap around in a circle, although as the circle traces out, we're going to move up the z-axis. So we're moving up the z-axis as we go throughout, and this path right here is called a circular helix. So this is an example of a vector valued function. It takes a real variable, the t, and it gives out a vector in the end, a point in the plane or in space. So along the lines of vector valued functions, we have some things that we're going to carry over from single variables, and that first is domain. If you look at the domain, we just need to look at the domain of each individual component. So for example, the domain on this previous one, well, the x coordinate is defined for all t, the y is defined for all t, and the z is defined for all t. So the domain of this function is going to be all reals, because there's no value you can plug into here that'll make anything undefined. If we look at a slightly more interesting function, let's say we've got r of t is, let's use standard vector notation, let's say we've got t over t squared minus 1i plus secant t j minus ln of t k. If we look at the domain of this function, well, first off, from the first component, I see that t can't be 1 or negative 1, because that would make the I component undefined. Next up, the j component, in order for this to be defined, we need to make sure secant is defined. Well, secant is the same thing as 1 over cosine. So we're looking for all the places where cosine is 0. Cosine is 0 at pi over 2, at 3 pi over 2, at 5 pi over 2, and so on. So all those multiples of pi plus pi over 2, none of those are allowed in our domain. And then for the last part, right here, ln of t, well, t can't be negative, and it can't be 0, otherwise ln would be undefined. So we also need that t is greater than 0. Not 1, greater than 0. So it looks like our domain, if we were to throw all these things together, is we've got t is greater than 0. And now since it's greater than 0, we can kind of ignore the negative 1 over here. So t is greater than 0, but t is not equal to 1, or pi over 2 plus n pi. So if we were to sketch out the domain on this, so we're starting out at 0. Now 0 we're not including, so we'll have an open circle at 0. and open circle at 1, but we're going to fill in everything in the middle. And then at pi over 2, we have another open circle, and then again at 3 pi over 2, and again at 5 pi over 2, and again at 7 pi over 2, and so on. And we're going to fill in all the gaps between all those open circles. So that gives us our domain for this function of more than one variable. Okay, so range you could look at also, but the range is much harder for functions, for vector valued functions, because the range is going to be some subset of two dimensions or 3 dimensions, and getting an actual formula for what the range is actually really just plugging all the t values in here. So we really won't look at range in the sense that you might have in previous classes, but we will look at limits. So to get the limit of a function of more than one variable, well, there is a formal definition. This is that the limit as t goes to c of r of t is defined to be L. Now L has to be a vector because this is a vector valued function. This right here means given any positive number epsilon, so that you can think of as the tolerance in the range, in the vector side of things, there is a positive number delta. So think of this as the tolerance in your domain, how close your t values will be to the limit point. So that as long as the distance from t to the limit point is small, it's within delta, as long as we're close to c, then the function in this case is r, then r of t minus the must be close to the limit. Now when we say close, the absolute value doesn't make sense here because these are both vectors, so we use norm or magnitude. So this is the same as the Calc 1 definition of limit, the epsilon delta definition of limit, although instead of absolute values we have magnitude, we have norm. What this turns out to be is that if you have any reasonable function, if you look at the limit as t goes to c,